Hello everyone, this is our video example related to our lecture where we talked about the degree of freedom analysis. This is question 4.24 and we're going to do parts A, B, and C on page 180. Go ahead and turn to that page, read up on this question, and then follow along with this example. In this example, we have a liquid mixture that contains 60 weight percent ethanol, 5% solute, and the balance is water. We are told that a stream of this mixture is going to be fed to a distillation column operating at steady state. Product streams emerge at the top and bottom, so we have a top stream emerging and a bottom stream emerging. We have a column design that calls for the product streams to have equal mass flow rates, so that's a process specification given to us. And the top stream should contain 90 weight percent ethanol and no solute. The part A requires us to assume a basis of a calculation, draw and fully label the flowchart, do a degree of freedom analysis to make sure that we can actually solve this problem. And part 2 requires us to start to solve for some of the the mass fractions and the ratio of the ethanol in the feed to that leaving in the product stream. So if you notice why we get to pick our own basis and not worry about how it affects the solution, if you look at what we are called to calculate in part B, we're called to calculate compositions, so mass fractions. If you recall, for mass fractions, it doesn't matter, the composition of a stream will not change whether you scale up or down, whether the process is scaled up or down. So it doesn't matter what basis we pick. The last thing we're asked to calculate is some ratio of the ethanol in the feed, in the bottoms to that in the feed. Again, that is a ratio that will not change regardless of the basis that we picked. So it doesn't matter which basis we picked. In part A, we can pick whatever basis we want. So let's go ahead and start drawing our process flow diagram. Just a quick note, I didn't add C on here. We'll do C later after we have finished this part. C is related to the linearization of an equation. So let's go ahead and draw our process flow diagram. Here's our diagram. We have a distillation column, we have a feed coming in, we have two streams coming out, a top stream and a bottom stream. So we have the skeleton of the process flow diagram. Go back to the question line by line and try to transfer whatever information that's given to us. We are given the composition of the feed stream. We have 60% ethanol, 5% solute. The remaining would be 35%, and that's water, so we can put that in here. In this case, since I have everything in that stream, I'm going to pick my basis as the feed as well. And I'm going to pick it as 100 kilograms per hour. So that's my basis. I have all the mass fractions of every single component in there, and I can label that right away. After that, we know that the product streams emerge at the top and the bottom. The column design calls for the product streams to have equal mass flow rates. So the mass of the top stream should equal the mass of the bottom stream. And the top stream needs to contain 90% ethanol, no solute, which means the remaining 10% has to be water. So we are given the composition of the top stream as 90% ethanol and 10% water. That's all we are given in this question. In terms of the top stream, we already have the compositions. What we are missing is the overall flow rate. So now we have M sub T, that's one of our unknowns. In the bottom stream, we have absolutely nothing that's given to us. What we do know is that we have all three components in there. We have the ethanol, the solute, and the water. So there's two ways we can label this. We can label it as the overall flow rate, MB, and the mass fractions of each component. Or we can label it as the actual mass flow rates of each individual component. In this case, what would make most sense is actually to label it this way, which is our mass flow rate and then the mass fractions. The reason is because if you look at the specification that's given to us, it says that the top and bottom stream must have equal mass flow rates. By writing it this way, we can write our specification easily as MT equals to MB. If we had written it the other way, where we have MEB, MSB, and MWB in our bottom stream, writing the specification would be cumbersome and difficult to use because what that would mean is MT is equals to the sum of the three masses in the bottom stream. So by labeling it this way, it's going to make our lives a lot easier. Once again, it's one of those things that with more practice as you're doing the problem, you might have labeled it one way, and as you try to solve it, it gets really difficult. You might realize that maybe if I had relabeled the other way, it would make my life a lot easier. So just go ahead and get more practice as you go through the problem sets. So we have fully labeled the diagram. Let's circle our unknowns, and we have our 5 unknowns. So the next step, rather than jumping into solving, let's do a degree of freedom analysis. Here are our 5 unknowns. So the first thing is to count the number of unknowns. We have our 5 circled variables right there. The next thing is to figure out how many material balances we can write, and that will be the number of species we have. We have ethanol, solute, and water. So we have 3 species. So we can write 3 species balances. Remember, it's not that we can just write the species balances. We also can use an overall balance. In general, an overall balance is easier to write and easier to solve as well. It's just that once you use an overall balance, you only have 2 other balances you can use. The next thing we can look at is process specification. We know that we are given one of them, which is the top and bottoms must have the same mass flow rates. So we have one process specification. And the last thing we have is a physical constraint. The sum of mass fractions in the bottoms have to be equal to 1. So now we have 5 minus 3 minus 1 minus 1. That will give us our 0. Degree of freedom tells us that we have these 5 unknowns that will be able to be solved for by writing 3 balances, using the process specification given, and using the physical constraint that we have, that the sum of x has to be equal to 1 in the bottoms. So now let's go ahead and start to solve this problem. Here's our diagram, and here's the degree of freedom again. Usually, in general, you will look for the process specifications and physical laws first to see if you can actually solve those. Those are generally the ones that you might be able to solve for right away. But down here, as you look at the process specification, you realize that you can't do anything because you don't know MT and you don't know MB. So there's not much we can go on except to use our balances. So let's write our overall balance. 0 equals to in minus out. We have MF coming in, which is 100, and then we have MT and MB as our unknowns. So in this case, we have 2 unknowns down here, but you'll realize that these 2 are the same unknowns as our process specification. So we can use our process specification and solve the overall balance simultaneously with our process specification, and you can see that they are both 50 kilograms per hour. Many of you have probably jumped ahead on this. You knew that 100 was coming in, those 2 have to be equal, so it has to be 50-50. And that is fine. What I'm presenting down here is more a step-by-step way of looking at the degree of freedom without jumping ahead and partially solving some of the problems right away. As our problems get more and more complicated, you are going to be less and less able to do so. So make sure to learn the degree of freedom properly as we are doing it right now. So once we have done this, remember we have used one process specification and we have used one balance, which means we have 2 more balances to go. Let's go ahead and do our solute balance. We have solute coming out in the feed, and we have solute coming out in the bottoms, but not in the top stream. So with that, you realize that we can solve for an unknown right away. Here is a case where the reason why I picked a solute balance is because the top stream has no solute, which means that the equation that I'm going to write is going to be a lot simpler and more likely to contain less unknowns. And sure enough, it turns out to be one where we can solve for an unknown right away. By solving that, you see that the mass fraction of solute in the bottoms is 0.1. We have one more balance to go. You can either use the ethanol balance or the water balance. So I'm going to do the ethanol balance. You have ethanol coming in the feed, ethanol coming in the top, and ethanol coming in the bottoms, but you realize you only have one unknown left, which is our mass fraction in the bottoms, and you can solve it as 0.3. And after that, you can, if you want to, you can solve for the last unknown, which is our mass fraction of water, by using our physical constraint. So 1 minus 0.1 minus 0.3 is equal to 0.6. But if you look at the question, we actually don't need that. What it asks for is the solute composition, the solute mass fraction, the ethanol mass fraction, and we want to know the ratio of the ethanol in the bottoms to what is fed into the column. So the amount that is in the bottoms is the mass fraction in the bottoms multiplied by the bottoms flow rate divided by the amount that's in the feed. We already have all of those numbers. We just plug in those numbers and we see that 25% of what is fed came out in the bottoms. All right, so now we have solved the entire material balance problem. There's one additional part to this question which is going to relate to what we have done where we linearized an equation. But now we're going backwards. What we have here is an analyzer to determine the composition of the ethanol water mixture. Everything so far we have done it's been nice. We just give you the values to say that this is the composition of ethanol. This is the mass fraction of ethanol in this stream. but practically there must be some way for us to be able to do that. So there are different tools you can use. In this case, we're not actually told what the tool is or how it works. We're just told that there's an analyzer that's available. So how do we figure out the mass fraction from here? You will actually generate a calibration curve. So what is being done is you will have different compositions ranging from 0% ethanol to 100% ethanol, pure ethanol and pure water. And you will get analyzer readings for a bunch of different mixtures in between and generate a calibration curve using this analyzer. It turns out that the calibration curve is a straight line when it's plotted on the log axis of mass fraction of ethanol, which is Xe, versus the analyzer reading. Remember that in terms of how we describe a graph, we say y versus x. So when it says the mass fraction versus the analyzer reading, it means the mass fraction is on the y-axis, the analyzer reading is on the x-axis. But in this case, it is on the log scale, so both of them are on the log scale. We are told that the line passes through 2 points, so we have 2 of these calibration points. We are told to derive an expression for x as a function of r based on this calibration data that we are given, and use it to determine the value of r if the based on the top product stream. So if you recall, the top product stream has 90% ethanol, so Xe is 0.90. We'll get there once we have developed the equation. So let's visualize what this calibration curve looks like. It is a log-log scale, so when we talk about the graph, we are talking about a plot of mass fraction of ethanol versus reading. They are both on the log scale, which means we are talking about the log of the mass fraction versus the log of the reading. We are told that the log of this log-log plot is a straight line. And we are given 2 different sets of points on there. Let's put them on here. When r is equals to 15, Xe is 0.100. Because this is log scale, we need to make sure to log all the values on there. And the second point is 38 and 0.400. So now, what we need to do is to develop a calibration equation. What we have is a straight line, so we can write an equation for this straight line. But the equation for a straight line is y equals to mx plus b. What is our y? Our y is our log of Xe. What is our x? Our x is our log of r. And so we have an unknown m, we have an unknown b. What we are trying to do is to develop a calibration equation x as a function of r. What you can think about this way is we are starting now with a linear equation and then making it nonlinear. So this is the backwards process of what we have done in the earlier lectures, where we are given a nonlinear equation and you are told to linearize this equation. So we're going through the process backwards. When we have an equation that looks like this, the first thing you can do is to use the log rules to move the m to the power. And now we have this. To get rid of the log on the left-hand side, I'm going to take 10 to the power of both sides. So 10 to the power of left-hand side is equal to 10 to the power of right-hand side. And I'm going to use one of the rules, which is 10 to the power of a plus b is equals to 10 to the power of a times n to the 10 to the power of b. So I'm able to split up the right-hand side in such a fashion. Then 10 to the power of a log is just that function itself. So now that just gives us our Rm, and we keep the 10 to the power of b right here, down here. But 10 to the power of b, we know that b is a constant, so 10 to the power of b is just another constant, and we can just call it b prime. And here is our calibration equation. You may recall that this could be a nonlinear form of equation where we have, this is our y, and this is our x, r is our x, and you are told to linearize this form, and that's just moving upwards or moving backwards to what we just did. Now, given the 2 data points, we can find our b prime and our m. There's a couple of ways to do it. What I'm going to do is just go back to the linear form, because m in the linear form is essentially the slope of this line. So let's just calculate the slope of this line. It's just the rise over the run. So the rise is log of 0.4 minus log of 0.1. The run is log of 38 minus log of 15. We have the slope of that line. Once we have the slope of that line, we can put it back into that equation and use either one of those points to solve for our b. I'm going to use the log 15 log 0.1 point to find the intercept b. Plug in the y and x values in here, plug in the m that we have. Now we can solve for our b, and it's minus 2.754. But what we want is b prime in our calibration equation, and b prime is 10 to the power of b. So we have that is 1.762 times 10 to the power minus 3. So we have our B prime, now M, we just put it into our equation, and here's our calibration equation. Note that there's a bunch of different ways you can solve for your B prime and M. You can actually solve for it from this equation right here, because you know two data points. You have 15 and 0.1 and 38 and 0.4. So you could use that equation and solve two simultaneous equations as well. You should be able to get the same answer. Okay, so now we have our calibration equation. We know that XE is 0.9 in our process. So now we need to calculate what R is. So all we need to do is to put XE as 0.9 into here, rearrange the equation and solve for R, and you see that the analyzer reading should give us a value of 65.5. So that's all we have for this example. Hopefully it's helpful in terms of how you will set up the problem, do a degree of freedom analysis, write out the equations and solve them in an efficient manner. And then in this case, we have more practice on linearizing an equation, or in this case, going backwards, the backward process of that. Work hard, be smart, and I'll see you next time.